Welcome back to Pre-Calculus Unit 8. We are here in Learning Target 8D exploring the graphs of different polar function families. In our last lesson we talked about circles and lines, and today we're going to talk about the spiral of Archimedes. So our first slide here has a bunch of examples of different spirals of Archimedes. And you can see that they all just kind of look like snail shells or spirals that start towards the middle of the graph and then wind outward. And they're called spiral of Archimedes simply because Archimedes was the Greek mathematician who first studied and described them. So you have examples here of 6 different spirals and their equations, and we want to look at what patterns we observe. So the first thing we want to notice is the overall format of the graph. All of these have the form r is equal to some coefficient, a theta, and then a constant added on at the end. So here this would be a coefficient of 1, a theta, and constant 3. We could have 2 theta, constant 3. We could have 1 theta, constant 4. So the first thing to notice is the overall format of these. They all have the format r is equal to some coefficient multiplied by the angle plus some second constant at the end. So r equals a theta plus b would be the general format of the graph. And so we want to know what is the effect or the outcome of each of these two different constants. As I change the coefficient on theta, what happens to my graph? As I change the b value, as I change the constant added on at the end, what happens to my graph? So let's look at these first 3 examples off the top. I see 1/2 theta plus 3, I see 1 theta plus 3, and I see 2 theta plus 3. So these all have the same constant. They all have the plus 3 added on at the end. And that allows us to just focus on what is the effect of the leading coefficient. How is the shape of the graph different when the angle is multiplied by 1/2 versus 1 versus 2? And what I observe is that it has to do with the width or the tightness of the spiral. When I have 1/2 theta, this is a very tight spiral. You can see lots of coils all pretty close to each other, and that distance between one curve and the next is pretty small. When I have 1 theta, now the distance between one curve and the next is a lot bigger. And then when I have 2 theta, this is a much wider spiral yet. I even went off the graph before I came back around, but if I were to follow the pattern, that would be approximately the distance between coils within my spiral. So we can see from this that the a value or the coefficient on theta has to do with the width or the tightness of each coil. Now let's look at my second set of 3 graphs here. All 3 of these have the same coefficient. These all have a width of 1. They all have 1 theta, 1 theta, 1 theta. And that allows us to focus on what's the effect of the second constant. How are these graphs different from each other when it has plus 0 versus plus 2 versus plus 4. And you can see that these graphs all have approximately the same shape. They are all pretty much the same spiral, but look at where they start. This one starts at the origin. This one starts at a radius of 2. And this one starts at a radius of 4. Coincidence? No. This one starts at 2 because it has a plus 2 in the equation. This one starts at 4 because it has a plus 4 at the equation. All of these up here on the top that were plus 3, they all start at the same spot right there at 3, halfway between 2 and 4. They all started at 3. So that shows you the effect of the second constant in the equation, and that would be the starting point of the spiral. So to summarize all of this, equations have the form r equals a theta plus b. So a is the leading coefficient, and that determines the tightness of the spiral. The bigger the coefficient, the bigger the distance between the curves, and the wider the spiral is. So if you have a small coefficient, something like 1/2 theta, then it's going to be a very tight spiral with a small distance between the curves. If you have a big coefficient, something like r equals 4 theta, then it's going to be a very loose and wide spiral with a lot of distance between each curve. And then the b value determines the starting point of the spiral. In other words, what's the radius if the angle is 0? And that makes sense because if the angle is 0, then this whole term would become 0, and you just have r is equal to the b value. So for these types of graphs, what you'll be asked to do for your learning target is mostly matching. So you'll be given a set of graphs and a set of equations, and you want to match based on the starting points and the relative width or tightness. So an example like this, we have 4 different equations and 4 different graphs, and we want to match them up. The 2 things that you're going to be looking for are, again, the starting point and then the width of the spiral. So looking at where these graphs start, that's going to be our first step. And I noticed that this is scaled by a factor of 2, 4, 6, 8, 10. So right there, that would be a starting radius of 1. This graph over here on the right also has that starting radius of 1. This graph down here has a starting radius of 1, 2, 3, as does this graph here, a 1 and a 2 and a 3. So remember that that starting radius comes from the b value in the equation. So these first 2 have a b value of 1. These bottom 2 have a b value of 3. So that is going to match equations A and C versus equations B and D. Now let's think about the tightness of the spiral. How long does it take for me to go from one curve to the adjacent curve? So on these 2 on the left here, notice how wide the spiral is. I am going off the graph before I even come around to my next curve. So if I were to follow this around, just kind of eyeballing the pattern here, looks like it goes something like that. So the width of my spiral would be from here to here. So these both are wide spirals, which means that they have a comparatively large A value, a comparatively large leading coefficient. These 2 over here on the right, these have a much shorter distance between loops of the curve. So when you have a short or a tight spiral like this, a narrow distance, so to speak, that means that they have a small A value. And you can't tell just by looking at the graph exactly what the value of A is, but we can compare them with our possible equations here. Equations A and B have a leading coefficient of 1, so that would be the smaller possible A value. And equations C and D have a leading coefficient of 3. That would be the larger possible A value. So putting this all together, this first graph has a starting point of 1 and a large A value. So that would be equation C. Starting point of 1, 3 being the larger of the 2 possible A values. So this graph matches equation C. Moving over to the right, this is a starting point of 1 and a narrow or a small A value. So that would be graph A. Starting point at 1 and the smaller possible leading coefficient, graph A. On the bottom left, I've got a starting point of 3. So I'll need a plus 3 in my equation, and this is a wide or a loose coil, which means a larger A value. So between the 2 remaining equations, option D is the one that has the larger A value. So this one here on the bottom left matches equation D. And then lastly, we have this one here with the starting point of 3, matching the b value of 3 and the narrower or smaller a value, the leading coefficient of 1. So that matches up with graph B. So that is how you would go through the thought process of matching spiral graphs with their equations. You can tell what the b value or the final constant is by looking at the starting point on the graph. It's a little bit like looking for the y-intercept on a linear function graph. You can't tell the exact value of the leading coefficient by looking at the graph, but you can match whether it is big or small compared to a different equation. So the wider the spiral, the looser the spiral, the bigger the leading coefficient. The narrower, the tighter the spiral, the smaller the leading coefficient.